Okay, so a couple more things about covariance. I want to talk about the formula that we use a lot for covariance, and I want to talk about covariance and correlation. Okay, so the formula. Remembering from the last video, we've got the definition um, of covariance. That is the expected value of the product of each variable's distance from its expected value there. Once again, my y's are looking a little too much like x's. Make sure that that is actually y there. That's the definition. In the last lesson, we talked about the logic behind it, and the definition is really good for seeing the logic, but for actually doing derivations and calculations, we almost always rewrite this as expected value of the product of x and y minus expected value of x times expected value of y. Okay, so the expected value of the product minus the product of the expectations might be a way to think about this. Or if you wanted to keep the notation completely parallel here, you could say that the covariance is expectation of x times y minus x bar y bar. So this is another formula in which we've got a term that is a function of the two random variables, and then we're subtracting off a number that comes from their expected values, the product of expected values. Okay, so this is a formula for covariance. And we'll go through the proof in workshop. It's all these proofs have kind of like a similar feel to them, so I think it'll feel familiar to you. Okay, and then I want to talk about correlation. So the thing with covariance, like regular variance, is it doesn't really have natural units. And so what that means is with covariance, we can be interested in sign, and often that's really kind of the main thing we care about. Is it positive or is it negative? But the magnitude by itself is tricky to interpret. So when we are interested in saying something about how strong the relationship between x and y is, we look at the correlation coefficient, which is something that we get from the covariance and the standard deviations. So if we want to interpret how strong the relationship, be it positive or negative, between x and y. Okay, so I'll just write the formula here. So the correlation coefficient, we almost always represent it with, that's a Greek letter rho. It looks sort of like a curly P. So the correlation between x and y is the covariance, x and y, divided by the standard deviation of x times the standard deviation of y. Okay, so it's just putting in those standard deviations to sort of correct for the variation in the individual variables there. Rho is always between -1 and +1. Okay, so if you have a correlation of -1, those variables are perfectly correlated negatively in the sense that if you know one, you know the other, but the relationship is negative. And similarly, correlation of 1 is they are perfectly positively related. Again, sort of just putting things in context, when we're actually interpreting real data like you would in a substantive class, we're probably going to be talking in terms of correlations. We actually care about the strength of relationships that we care about. In methods classes, we're just trying to understand the logic behind statistical estimators. We're more likely to talk about covariance. Okay? So for the rest of 200B, we're going to be bringing up covariance now and then, not paying too much more attention here to correlation. But just before leaving it, why don't we calculate it for the city council school board example. Getting a lot of mileage out of that example. That's fine. It took a lot of work to set up, so let's keep going with it. Remember, we found that the covariance between the median voter on the city council and the median voter on the school board, that's where X's and Y's are, was 0.1875, and the variance of X was 2.23, the variance of Y 0.2475. I'm not sure we actually calculated that before, but that is in fact what it is. And so the correlation coefficient for that example between those two random variables would just be that covariance up here divided by the standard deviation of X times the standard deviation of Y. And what does that come out to be? 0.2524. So it's a modest positive correlation. Okay. One more thing to go over with covariance, but I'll save that for the next video. So I'll see you then.